Welcome back. Section 2.1, Force. A force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The state of motion may be one at rest or of moving uniformly along a straight line path. For example, a hockey puck at rest on ice remains at rest until a force is exerted upon it. Once moving, the hockey puck sliding along the ice will continue sliding until a force slows it down. Key concept: a force is needed to change the object's state of motion. Net force. Most often, more than one force acts upon an object. The combination of all forces acting upon the object is called the net force. The net force on an object changes its motion. For example, suppose you pull horizontally on an object with a force of 10 pounds. If a friend assists you and also pulls in the same direction with a force of 5 pounds, then the net force is the sum of these forces, or 15 pounds. The object moves as if it were pulled with a single 15-pound force. However, if your friend pulls with a force of 5 pounds in the opposite direction, then the net force is difference of the two forces, or 5 pounds towards you. The resulting motion of the object is the same as if it were pulled with a single 5-pound force. This is shown in Figure 2.1, where instead of pounds, the scientific unit of force is used, the Newton, abbreviated capital N. Figure 2.1. The net force depends on the magnitudes and directions of the applied forces. When you hold a rock at rest in your hand, you are pushing upward on it with as much force as the Earth's gravity is pulling down upon it. If you push harder, it will move up. If you push with less force, it will move downward. If just holding it at rest, as shown in Figure 2.2, means the upward and downward forces of it add to zero, the net force on the rock is zero. Figure 2.3. The upward tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is zero. Burl Gray, who first introduced the author to the concept of tension, shows a 2-pound bag producing a tension of 9 newtons. Tension and weight. If you tie a string around a 2-pound bag of sugar and suspend it from a scale, a spring in the scale stretches until the scale reads 2 pounds, as shown in Figure 2.3. The stretched spring is under a stretching force called tension. A scale in a science lab is likely calibrated to read this 2-pound force as 9 newtons. Both pounds and newtons are units of weight, which in turn are units of force. The bag of sugar is attracted to the earth with gravitational force of 2 pounds, or equivalently 9 newtons. Suspend twice as much sugar from the scale and the reading will be 18 newtons. There are 2 forces acting on the bag of sugar: tension forces acting upward and weight acting downward. The 2 forces on the bag are equal and opposite, and they cancel to zero. The net force on the bag is zero, and it remains at rest. Force vectors. In Figures 2.1 and 2.2, forces are represented by arrows. When the length of an arrow is scaled to represent the amount or magnitude of the force, and the direction of the arrow points in the direction of the force, we refer to the arrow as a vector. A vector is an arrow that represents the magnitude and direction of a quantity. A vector quantity is a quantity that needs both magnitude and direction for a complete description. Force is an example of a vector quantity. By contrast, a scalar quantity is a quantity that can be described by magnitude only and has no direction. Time, area, volume are all scalar quantities. We'll return to vectors in Chapter 5. Concept check. How can you change an object's state of motion?